We're talking about quantum computing, and we are exploring the strangeness that is quantum mechanics. And I want to walk through this example because this really does get at the heart of how weird this stuff is. Because once you understand that you can't understand it, or that it sort of undoes your perception of what reality is, then we can get into how to actually utilize this for computation. So this is an experiment called the delayed choice quantum eraser. And there's videos all over the place about this, but I'll give you my quick take. You fire an electron gun through a pair of slots on a screen, just like with the double slit experiment. But in this case, after that screen, you split them, right? You take the particle stream and you split it using a silvered mirror or something like that. So there are two copies of each stream, right, through those two different slots. Then you combine them on a wall, right? D0 is the place where the particles hit the wall and produce the interference pattern. So that's the regular experiment. Electrons go through slot A and slot B, and they interfere and they line up on the wall D0. Now, where it gets to be delayed is the second half of those beams. You send them through a bunch of mirrors and stuff into a detector down here, D3. This is just the very first part of it that I think is important to look at first. So ignore the rest of that for now, but you send it down to a detector which is farther away than that initial screen. Now, what makes this strange is if you turn on this detector, you know which slot the electron went through. If you do that, that means that the pattern at D0 becomes a pile instead of an interference pattern. And you think about what that means. That means that the electrons, as they hit the target D0, they are going to hit in a particular place, but after they hit, the detector at D3 can set them into either a pile or an interference pattern. It's not like they change state, right? The electrons hit the screen in a particular place. But the point is that the electron knew where it was going to hit the screen after it hit the screen. The measuring the which slot the electron goes through at any time after will cause it to collapse, cause it to not interfere with itself, and end up as a pile. The interference pattern gets destroyed even after the photons arrive at the detector. It's strange, but it gets stranger. If you think you understand quantum mechanics, you don't understand quantum mechanics. This is a famous quote. Richard Feynman says this because this stuff is really, really strange. And every time you look at it, it gets stranger. So here's the eraser part of the delayed choice quantum eraser. So this is the delayed choice part, right? You measure the which slot the electron went through after it hits the screen, and you still collapse the wave function that way. Now, the experimenters recombined these two beams into one. This little triangle here with detectors D1 and D2, this is a way of taking those two beams that are separated from slot A and slot B, and then putting them back together such that you don't know which electron went through slot A or slot B. If you measure at D3, you know, you have information about which slot the detectors, or which slot the electron went through. That means that you've measured it, and that means that the wavefront at D0 collapses. If you turn off that detector and recombine the beams into D1 and D2, you lose that information. You throw away that information, and the interference pattern reappears. What makes this ridiculously weird is that we know that at D3, the waveform had already collapsed, right? Measuring at D3, which is after the screen, collapses the waveform. But if we take away D3, then the waveform reappears. The interference pattern reappears. It doesn't make any sense. Every time you think about it, it gets weirder and weirder. A few more notes on this kind of stuff. So there are a couple of different ways to interpret quantum mechanics. Some folks believe that this means that things don't have properties until they're measured. So they exist in a superposition of states such that they really are multiple things at the same time until they're measured. That's disturbing. Another way of interpreting this is that these items, they have properties that are real and they interact with the world, but we can never measure them by virtue of features that they have. Super weird. So all of this is to say quantum mechanics is weird, but we're going to make use of this weirdness in order to do some computation. We're going to do this with an idea called a qubit. We're going to take a single electron, for example, with a quantum spin state, quantum spin up or spin down. However you want to interpret this, there are quantum computers that use lots of different kinds of particles, but for this example, we'll use an electron, and we're going to manipulate the superposition of its state. So we started out as spinning up or spinning down or whatever, and then we're going to manipulate it in such a way that it will be able to do some mathematics, do some interesting work. Examples of it, like the phosphorus in a silicon transistor. This is why this is difficult and expensive, is that in order to do this, to be able to manipulate the quantum state of these particles, you have to get them to supercooled states. You have to get massive magnets to be able to mess around with them. But if you do this, then you can influence superpositions, and then you can measure these superpositions and do math in this way. We are going to operate in these qubits to do work. We are going to manipulate the superposition of these quantum states in order to do work. But the problem is we have to be really careful about how we measure, because as soon as we measure, right, the delayed choice quantum eraser tells us that as soon as we measure, regardless of where we are in the process, if we measure something, we collapse the waveform, we no longer have the superposition, and we can't make the superposition do work for us. So whatever manipulation we're going to do to a superposition, it has to be reversible. We're going to put it through a gate, for example. That gate can manipulate it, but it has to do it in a way that is reversible, because that way we allow the superposition to continue. We don't collapse the state, we allow the superposition to continue. So in the next little video, I will show you some examples of quantum gates and how they work.